Welcome students, welcome to the solid mechanics class. So today we are going to start a chapter that is principal stresses and strains and mode circle. So in this chapter we will going to learn that what is principal stresses, what is mutually perpendicular direct stresses, and how to draw the mode circle. Okay, so let's start. So as you can see in this picture, this is CD is a shaft CD. The axis of this shaft as shown in this figure, this is the axis of this shaft, this CD shaft, and P is the force is acted along with this axis. Okay, and this LL is the axis which is perpendicular to this axis, to the axis of the shaft. Okay, LL axis is perpendicular to the axis of the shaft, okay, or perpendicular axis, whatever you want to say. And this MM is another axis which is inclined at an angle theta with this LL axis. Okay, MM axis is inclined at an angle theta with this LL axis. Okay, so if we cut this rod along this MM axis like this, so the cross sectional area along this MM axis will be A by cos theta. A is the actual cross sectional area, and if we cut this shaft along this MM axis, the cross sectional area will be A by cos theta. So now if we imagine this is another shaft, okay, imaginary shaft, and this is the axis of this imaginary shaft, and MM is perpendicular to this axis, and the cross sectional area is A by cos theta. So the stress, that is normal stress, which is acted along this cross sectional area or along this axis perpendicular to this cross sectional area along this axis is sigma n. The normal stress is acted along this axis, this imaginary shaft axis is sigma n, and which is perpendicular to this cross sectional area, that is A by cos theta. Okay, again I am explaining. This is the, suppose this is the shaft, the actual shaft, this is the axis of this shaft. LL is perpendicular to this axis, which is perpendicular 90 degree, and MM is inclined at an angle theta with this LL. Now if we imagine another shaft along this MM, that means this is the axis of this imaginary shaft, and MM is perpendicular to this imaginary axis. So the cross sectional area of this shaft is A by cos theta, just like this. This is the original shaft. If we cut this shaft along this MM axis like this, which is inclined at an angle theta with this LL, so the shaft is looks like this. This cross sectional area is A by cos theta. This is A, the cross sectional area, and this cross sectional area will be, once again, and this cross sectional area will be A by cos theta. Okay, so now let's talk about the force. Let's talk about the force. Okay, as you can see, the force P, which is acted along this axis of the original shaft, okay, and sigma n is the normal stress which is acted along the axis of the imaginary shaft. Okay, so this is the P force, the original force. Okay, the perpendicular of this axis is LL, and MM is inclined at an angle theta. So the perpendicular of this MM axis, the force which is perpendicular to this MM axis is P cos theta. okay, according to this diagram. Okay, this is a basic trigonometry, and parallel to this cross sectional area is p sin theta. Perpendicular to this cross sectional area is p cos theta, and parallel to this cross sectional area is p sin theta. Okay. Now if we resolve the force along this the perpendicular to that means along this axis, if we resolve the force along this axis, we get a by cos theta into sigma n is equals to p cos theta, right? A by cos theta into sigma n is equals to p by cos theta. A by cos theta into sigma n equals to p cos theta. So the sigma n value, the value of the normal stress along this axis is nothing but p by a cos square theta, p by a cos square theta. So this is the value of the normal stress which is acted if the cross sectional area is inclined at an angle theta with the original cross sectional area. Okay, so this is the value of the normal stress. Okay, so further if we want to resolve this parallelly, if we resolve the force parallelly, then let's see what we'll get. For parallel resolving forces, or parallel resolving forces, we get tau is the shear stress. Why this shear stress comes? Because the stress which is acted normally with this cross sectional area, we called it normal stress, and the stress which is acted parallelly with this cross sectional area, we called it shear stress. So the force which is related to this shear stress is p sin theta, which is the parallel force of this cross sectional area. So the value of shear stress, or the value of tau, will be tau into similarly tau into a by cos theta equals to p sin theta. So the value of tau, the shear stress, will be p by a sin theta cos theta. So this is the value of shear stress tau of an cross sectional area which is inclined along at an angle theta with the original cross sectional area. Okay, this is the value of the shear stress. So from these two relation, that is from the sigma n and tau, from this two relation we can comment that the when the rod is subjected to pure tension, that is both tensile and shearing stresses are produced in a material under direct compression, the corresponding stresses will be compressive and shearing. Okay, now for to find out the maximum shear stress, shear stress, we have to convert this theta sin theta cos theta into the sin 2 theta like this. That means tau equals to if we multiply with 2, this numerator and denominator value, so we can write the shear stress in this fashion, that is p by 2a into sin 2 theta. We can write p by 2a by sin 2 theta. So to find out the maximum value of the shear stress, that means for sin 2 theta equals to 1, that means theta equals to 45 degree, we get the maximum value of the shear stress, that is tau max equals to P by 2A. Okay. Now the stress is due to pure shearing. Okay, suppose let's assume a block LMNP is a block of depth or height 1. That means this is a 2D block, okay, because its depth or height along this perpendicular to this page is 1. Okay, so the volume of this block is only LP into LM. Okay, so and also assume the shear stresses, that is tau xy, is acted in this fashion: tau xy along M to N, this tau xy along P to N, and tau dash xy along M to N, and tau dash xy along L to P. Okay, the shear stress is acted along this block like in this fashion. Okay, so the another thing is that the force, that means the resultant force, if we write the resultant force, that is the stress into area, that will be for this face and this face. First, this face and this face, the shear stress will be the force will be the shear stress tau xy into the area, that is LM, and the height of this block is 1, so that will be LM or ML, whatever, that is equals to, for this, tau xy into NP into 1. Okay, because the height is 1, or Pn. So you can see there is no resultant force, because the force acted in this side and in this side is same. Similarly, the force acted in this side and this side is same, because it's a rectangular block. The length of LM and length of NP is same, length of MN and length of LP is same, so no resultant force is acted on this block. Okay, first thing, from this figure we can write. So the couple due to this force, that means this force tau xy into ml into this distance mn, the force into this force into the distance mn distance, we get a couple. So let's see what is the equation for couple. Okay, so that will be tau xy into ml into mn. So this is the couple. Okay, because when two forces are acted in opposite direction, the two same forces, the same amount forces are acted opposite to each other, there obviously a couple is generated in for this kind of situation. This is a basic physics. So to balance this couple, the block we have to insert another couple. Okay, to balance this couple we have to introduce another couple, and that must be equal to this couple. The another couple which balance this couple, couple is acted in this fashion. This couple is acted in this fashion, and another couple which balance this couple will be acted in this fashion. Okay, so the another couple will be tau dash xy is equals to mn this is the tau dash xy, this is the tau dash xy into mn. Mn is the length into height, height is 1, so the area is mn into 1, so area into this stress, so tau dash xy into mn into the length, that is ml, so that becomes a couple. So this couple will be balanced by this couple. Okay, again this couple will be balanced by this couple. Okay, so we can this is the couple balanced equation, so we can write from this equation, that is tau xy is equals to tau dash xy. Here one thing I want to mention, that is the length of ml is equals to length of pn, and the length of lp is equals to length of mn. Okay, because it's a rectangular block. Okay, so that means this stress is equal to each other. So for equilibrium, the complementary shearing stresses, that is tau dash xy, must be introduced. Okay, for equilibrium stresses, the complementary shearing stresses, that is tau xy, must be introduced. So let's check another situation. In this situation, as you can see, MNPQ is the block, is a 2D block of height 1 unit height. So the cross sectional area AA, or the plane AA, cut this block in this fashion. This AA plane cut this block, this rectangular block, in this fashion. That means at an angle theta with the MQ, at an angle theta with the is inclined with this line MQ or ML. Okay, the AA plane is inclined at an angle theta with this ML. Okay, and the shear stress tau xy is acted in this both the side, because we have already seen that this tau xy and tau dash xy is same, so we have just written the tau xy. So the normal stress along which is perpendicular to this AA plane is sigma n, and the shear stress along this AA plane is tau. The normal stress along this AA plane is sigma n, and the shear stress along this AA plane is tau. Okay, so let's resolve this forces into the perpendicular to AA. Let's resolve the forces perpendicular to AA. So what we get, that is sigma n into the area. Area means sigma n is acted in this length ln AA or ln. So ln into the height, that is 1. So sigma n into ln, sigma l into ln, that is equals to tau xy into lm sin theta plus tau xy into mn cos theta. This is the tau xy. Okay, tau xy, the that means perpendicular to this ln. That means if we resolve this tau xy into this axis and into this axis, we get the perpendicular component of this tau xy is tau xy sin theta, because the value of tau xy in along this axis is tau xy cos theta, and along this axis is tau xy sin theta. For I am talking about this stress. So the force, that is tau xy into lm or ml, into along this axis is tau xy lm sin theta. Now for this side, tau xy into mn, the height is 1, so tau xy into mn, and the perpendicular axis and the perpendicular force, if we resolve this force into perpendicularly, we get, because this is the theta and this one is the 90 degree, so this is the value of tau xy mn cos theta. The perpendicular value for this side force, that is tau xy mn force, is tau xy cos theta along this axis. Okay, so tau xy lm sin theta for this side and tau xy mn cos theta for this side. Okay, so the normal stress, that is sigma n, is equals to tau xy into lm by ln sin theta plus tau xy mn by ln cos theta. Okay, so from the basic trigonometry, we can write, from the basic concept of trigonometry, we can write sigma n is equals to tau xy, that is the lm by ln, the lm by ln, lm by ln is equals to cos theta. The lm by ln, this lm by ln is equals to cos theta. Okay, into this sin theta. So tau xy cos theta sin theta plus tau xy. Now this is mn, sorry, this one is nm or mn, mn by ln, mn by ln is sin theta into cos theta. So tau xy cos theta sin theta plus tau xy sin theta cos theta. So the value of sigma n will become sigma n equals to 2 tau xy sin theta cos theta, or we can write sigma n is equals to tau xy sin 2 theta from the basic trigonometric equation. So again, now the maximum value of sigma n. So the maximum value of sigma n will occur when sigma n max, the maximum value of sigma n occur when the value of 2 theta becomes 90 degree or theta becomes 45, that is tau xy into sin 90 degree, that means 2 theta equals to 90 degree. So the value of sigma max, sigma n max value is tau xy. This is the maximum value of sigma n. Now the minimum value of sigma n and sigma n mean, the minimum value of sigma n will occur when the value of 2 theta is minus 90 degree, because we know that sine of minus theta is equals to minus sin theta. So that becomes tau xy sine of minus 90 degree, that means 2 theta equals to minus 90 degree. So sigma n minimum min is equals to minus tau xy. So this one's for the maximum value and this one's for the minimum value. Okay, so the significance of this maximum and minimum is that the when the for in case of tensile the sigma n max is equals to tau xy, and in case of compressive stress, that is equals to the sigma n mean is equals to minus xy. In other words, a case of pure shear is equivalent to direct tensile stress and direct compressive stress acting perpendicular to each other. Okay, in case of pure shear is equivalent to direct tensile stress and direct compressive stress acting perpendicular to each other. Okay, now let's resolve the forces parallel to AA. Let's resolve the forces parallel to AA. So let's see. So the parallel force along this AA plane is tau, this tau, the shear stress, into the area, that is ln into 1 is the height, so tau into ln, and that will be equals to this tau xy into mn along this direction, that means tau xy mn into sine theta. This directional component is sine theta, sine component, and for this stress, that is tau xy lm into cos theta. The component along this direction is cos theta. Again, tau into ln is equals to tau xy into mn sine theta minus tau xy into lm cos theta. Why minus? Because the direction of this tau xy and this tau xy is opposite to each other. That's why a minus sign comes. Okay, so let's write the equation. So as I have told, that is tau into ln, the shear stress along the ln, is equals to tau xy into mn sine theta minus, because the stress direction is opposite to each other, tau xy ln tau xy mn lm tau xy lm cos theta, tau xy mn sin theta minus tau xy lm cos theta. So the value of tau will be, so the value of tau is equals to, that is tau xy into mn by ln into sin theta minus tau xy lm by ln cos theta. Okay, so from the basic geometry we can write the mn by ln. The mn by ln is equals to sin theta, so that is sin theta into sin theta, this sin theta is this, minus tau xy into lm by ln is equals to cos theta into this cos theta. So the tau value, becomes tau is equals to tau xy sin square theta minus tau xy cos square theta. So we have already know this is the basic trigonometry formula. So we can write minus tau xy, tau equals to minus tau xy into cos square theta minus sin square theta. Okay, and that is equals to cos 2 theta. So minus tau xy into cos 2 theta. So tau equals to minus tau xy into cos 2 theta minus tau xy into cos 2 theta. So tau will be 0 when the theta is plus or minus 45 degree. So the tau at theta equals to plus or minus 45 degree, as theta equals to plus or minus 45 degree, the value of tau is equals to 0. Okay, so this is the stresses due to pure shearing. So let's talk about two mutually perpendicular direct stresses. As you can see in the right hand side figure, in this figure, LMNQ is a block, is a 3D block where the height is 1, so that becomes 2D, and the LN is a cross section at an angle theta. So let's find out the value of this normal stress and shear stress along this LN plane. Okay, and LN plane is inclined at an angle theta with this LM. Okay, so this is the representation of that triangular block. Okay, where the two perpendicular stresses, direct stresses, that is sigma x and sigma y, is acted here. So as we have done in the previous case, we will going to do the same. That is, first we will resolve this resolve these forces in normal to this LN plane. Then we will resolve these forces into parallel to this LN plane. Okay, so let's start. First of all, let's resolve these forces along this LN plane. So one second. Resolving normal to ln. So that becomes resolving normal to lm, that becomes that this sigma n, this is the normal stress, into the area, that is ln, into the height is 1, I have told. So sigma n into ln, that is sigma n into ln, is equals to sigma x into lm, this sigma x into lm into cos theta. That means sigma x into lm, sigma x into lm cos theta, plus sigma y into mn, this sigma y into mn, sigma y into mn sin theta, sigma y into mn sin theta. Okay, so this sigma x lm cos theta and sigma y lm sin theta comes from this geometry. Okay, this is the basic thing that I am not going to explain further. So the value of sigma n, the value of sigma n is equals to sigma x into lm by ln into cos theta plus sigma y into mn by ln into sin theta. So we can write sigma x. So from the geometry, lm by ln is the cos theta and mn by ln is the sin theta. So we can simply write sigma x cos theta into this cos theta plus sigma y into sin theta into this sin theta. So that is equals to sigma x cos square theta plus sigma y sin square theta. Okay, so now we are going to multiply 2 in the numerator and denominator from these two cases. So let's write sigma x by 2 into 2 cos square theta, similarly plus sigma y by 2 into 2 sin square theta. Okay, so we can write sigma n is equals to sigma x by 2 into, so the 2 cos square theta, the value of 2 cos square theta we can write 1 minus sin square theta plus cos square theta plus let's write in the next line sigma y by 2 into 1 minus cos square theta plus sin square theta, cos square theta plus sin square theta. Okay, so again by simplifying, that is sigma x plus sigma y, this sigma y by 2 plus sigma x into cos square theta minus sin square theta by 2 minus sigma y cos square theta minus sin square theta by 2. So the value of sigma n becomes sigma x plus sigma y by 2 plus sigma x into cos square theta minus sin square theta by 2 plus minus sigma y into cos square theta minus sin square theta by 2. Okay, now the value of the sigma n becomes sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta, because the value of cos square theta minus sin square theta is cos 2 theta, so that becomes cos 2 theta. So when theta is 0, when the value of theta is 0, the sigma n becomes sigma x. When the value of theta is 0, the sigma n becomes sigma x, because the value of cos 0 is 1. Okay. Again, when the value of theta is pi by 2, then the sigma n, when the value of theta is pi by 2, so the value of value of theta is pi by 2, so the value of sigma n becomes sigma y, because okay, so this is the expression for sigma n, the normal stress. So let's resolve the forces of Ln plane into parallel to itself. Okay, let's resolve the parallel forces of Ln. So by resolving parallel to Ln, the parallel stress is the shear stress. So the force is shear stress into the area Ln into 1, because 1 is the height of the block. So tau into Ln, so that is equals to sigma x into Lm sin theta minus sigma y equals to mn cos theta. So this minus sign comes because the direction of the forces is opposite to each other. Okay, so tau is equals to sigma x into Lm by Ln into sin theta minus sigma y into Mn by Ln cos theta. Okay, so this is the expression for tau, and the value of Lm by Ln is cos theta, and the value of Mn by Ln is sin theta. So sigma x cos theta into sin theta minus sigma y sin theta into cos theta. Okay, so the value of tau now we can again simplify this thing like sigma x minus sigma y into sin theta cos theta. This is the value of tau, so that becomes sigma x minus sigma y by 2 into 2 sin theta cos theta. Okay, so that becomes tau is equals to sigma x minus sigma x minus sigma y by 2 into sin 2 theta. So this is the expression of the shear stress along the Ln plane. Okay, so now the maximum value of shear stress occurs when the 2 theta, the sin 2 theta value is pi by 2 or theta value is pi by 4. So we can write tau max is equals to sigma x minus sigma y by 2 into sin pi by 2, or simply write the sigma x minus sigma y by 2. This is the value of tau max when the value of 2 theta is pi by 2, that means theta equals to pi by 4. The theta equals to pi by 4, the tau value is getting maximum for this case. So last one is the resultant stress. So let's find out the resultant stress. Resultant stress is nothing but sigma r resultant stress sigma r is equals to nothing but root over sigma n square, the normal stress square, plus shear stress square. This is the expression for resultant stress. And tan phi value is equals to tau by sigma n. The tan phi value is tau by sigma n, where phi is the angle which the resultant stress makes with the normal to the plane and is called the obliquity. Again, the phi is the angle which the resultant stress makes with the normal to the plane is called obliquity. Okay, so this is the expressions for two mutually perpendicular direct stresses. So in this lecture we have learned about the stresses due to pure shear and the stresses which are mutually perpendicular to each other, that means the direct stresses. So and we have also find out the different expression for direct stresses and the shear stresses. In the next lecture we will learn about the principal stresses, how to draw the how to find out the expression of major principal stress, minor principal stress, and this kind of things. Okay, thank you.